Okay, welcome to CM4269 Green and Sustainable Chemistry. This is the Green Chemistry lecture. Okay, in terms of what we're going to be looking at today, we're going to wander through these first two parts. This third part, we will look at some parts of that within the body of what we're doing, but largely these will be embedded as little mini case studies or examples in this and the next couple of lectures. For reading, as usual, there are a number of references embedded on the slides, but the course book, Lancaster, we're probably in chapters 1 and 2 at this stage. Right, I think that's done. No? Technology willing? Excellent. Okay, the next two slides you've all seen before, so we're in here at the moment, which is fine. And in terms of this slide, you also see every lecture. We're firmly down into here. There's none of the environmental chemistry and there's none of the biogeochemistry. Okay, so maybe the first question to ask is, what is green chemistry? I think the best thing to do here is let's simply look at a dictionary definition, and I won't read it to you. I'll let you read that. Second, let's maybe look at a definition from Yale. This was one of the places where green chemistry started. And finally, from somebody called Paul Anastas. He was the person that first came up with, well, may not be the first to have come up with the idea, but certainly the first to begin to build it and implement it. He's sometimes called the father of green chemistry. And there you go. Okay, so now we pause. I've not read these, you've read them yourself, but what this seems to tell me about the chemical industry is that maybe there's good processes and bad processes, or good products and bad products, or good ways of doing things and bad ways of doing things. So maybe we should start with trying to understand how we tell which are good and which are bad. And I am aware that those terms are hugely subjective, and that's quite deliberate. Okay, so we have a chemical industry. It does all of these things, makes most of the goods for the world's other industries to use, most of the chemicals. And in doing so, yes, it makes money. But yes, as well, if we go back to our context lecture, there's an awful lot of externality. There's a lot of environmental damage where the environment is paying, a lot of pollution, and obviously health issues as well. So let's move forward with what Paul Anastas set out as the 12 principles behind green chemistry, the things that green chemistry should be, basically, rather than what the chemical industry currently is. And again, there are various references at the bottom. Please do just look at them as you need to. Okay, the first principle is effectively prevention is better than cure. It's always better to prevent waste than to treat it or clean it up after it's been created. Now, what sort of handle do we have on this? How can we think about this? Well, one of the things that Anastas and others have set up are a series of metrics. Simple things that one can calculate to answer the question. For instance, how much waste am I producing here? So this is the first of those, and it's called the E factor. There's a pharmaceutical version of that, which is not quite the same actually, called the PMI, the process mass intensity, we'll look at in a moment. Okay, the abbreviations are all down here. Effectively, what the E factor is the ratio of the masses of the waste that you produce divided by the mass of the product you produce. So in this case, a low value of EF is better than a high value. A high value means that there's much more waste than product, which actually is the norm. But hang on a minute, how do we define waste? Well, if you think about everything you put into your, let's stick with a lab example, you've got your flask, you put in your reagents and your solvents and everything else you're putting in. You do the reaction, you add the other bits of reagent and whatever you're doing, and eventually after you've separated it and crystallized it, you end up with your product. Now waste is everything which is not your product. Water, solvents, raw material, reagents, absolutely everything. You might want to just pause for a moment and think about the organic preparations that you've done and what you think the ratio of waste is to your product. I mean, in my labs, I remember, I can't remember any specifics now, it's a long time since I did organic chemistry, but I ended up with maybe 0.5 grams of product after I'd crystallized it or before I'd crystallized it, and the amount of material I used to get that was quite huge. So numbers for EF can be quite high. I will just differentiate between EF and PMI. So EF is the ratio of the mass of the waste to the mass of the product. PMI is almost the same. It's the API in pharmaceutical terms is called the active product ingredient. So it's the drug, if you like. You might have a ibuprofen and a tablet that big. Only maybe 20 milligrams will be ibuprofen. The rest will be Paca and things like that. So it's the mass of the API, in this case the ibuprofen, and that's beneath the mass of all materials, including the product. Now, usually, as the product mass is quite small, actually, in practice, these two numbers may look the same or very similar, but actually, they're different. Okay, so that's great. Prevention is better than cure. We've got a little metric here to give us an idea of how much waste our product, our production of the product is making. And there is a line here. This line starts at the factory gate and ends at the factory gate. So we're not going back to think I'm using, I don't know, caffeine as one of my reagents. Where did the caffeine come from? We just start at the factory gate. Yep, here's the caffeine, and you begin from there. So if anything, these EF values, they're process dependent, obviously, but if you were to calculate the entire mass from produce your ibuprofen tablet or whatever, it would be much greater. The mass of waste will be much greater than the process mass of waste that we're dealing with here. Right, okay, let's continue. And the first principle was prevention is better than cure. The second encapsulates a term called atom economy. Synthetic methods should be designed to maximize the incorporation of all materials used in the process in the final product. So rather than using mass as the first index did, this literally deals with atoms, and it's a percentage metric, so it's multiplied by 100. And it's basically the relative molecular mass of your product. Okay, so this ratio is the other way up now because you haven't got waste on top, you've got product on top, divided by the relative molecular mass of all your reactants. So this is actually worth thinking about a little bit. This is rather different from the mass measure. You've all done, well, let's start from the beginning. Let's imagine we've got an organic synthesis and it's 100% efficient. I have never, ever done a synthesis like that. If I were to do that and then look at the ratio of relative molecular mass of my product divided by my reactants, pardon me, that tells me literally how much of the material that I've bought, maybe in a different form to how I bought it, but the material nonetheless that I've bought, I'm going to be throwing away. And this turns out to be a maximum number because most syntheses are not 100%. So again, it may be slightly underestimates, but it's dealing with a particular part of the process. And let's show you what we mean by looking at an example. So this is a halogenation reaction, and it's an alcohol with acid catalyzed sodium bromide to give you the bromoalkane here and some side products. Now, how are we going to do this? Right, I've reproduced the equation here with all of the numbers up so we can just add it all into a calculator. It turns out that our product here, where is it gone? There it is, has a relative molecular mass of 137. So I've put that there. Our reagents, on the other hand, the things on the left of the equation, have a relative molecular mass of 275. So the PAE is just the ratio of those multiplied by 100. It's about 50%. So again, even if your yield, your chemical yield is 100%, that is the impossibly wonderful reaction, you're still wasting 50% of the ingredients that you've paid for, not in the form, you bought sodium bromide and sulfuric acid, and you're throwing away sodium bisulfate, and water, but nonetheless you're still throwing the atoms away. So you're wasting 50% of the material that you bought, and deep holy joy, to add insult to injury, you're paying for the disposal. So that's the second principle then, which was effectively that of atom economy. The third principle, less hazardous chemical synthesis. This means wherever possible or practicable, you should be using synthetic methods that use and generate substances that possess little or no toxicity to human health and the environment. Now, this can be quite a tough call. And I suppose this is what green chemistry is about as we do these conversions, reaction by reaction. And yeah, we'll talk about that in a lot more detail. But let's start with the obvious problem. What if your product is a poison? What if you're making poisons? And actually, yeah, it happens a lot. I'm going to give you a particular example now of a slug killer. And I'm going to tell you a story, which is a green chemical story, but by accident. Okay, let's first of all look at what we're talking about. We're talking about slug killers, and there are a number of actives used in slug killers. It used to be mercury. It's now often methyl carbamate, also called methocarb. And I'd like to introduce you to something which is not known for this and is not a usual ingredient of slug pellets, which is urea, which is a plant fertilizer. And there are other actives as well. I mean, there are paraformaldehyde, there's quite a lot. Anyway, let's get on with the story. Okay, so here he is, the slug, gardener's best friend. Not. And slug pellets, which are often used as the first line of defense against slugs and snails. They're usually bright coloured, maybe pink, maybe blue, which is part of the problem. They're composed of usually cereal grains, which have been soaked and absorbed with either metaldehyde or methocarb, and a newer idea is iron EDTA. Right. What are the problems with these? Well, it's easier to ask where isn't there a problem, because the pellets are always bright blue or bright pink. Unfortunately, birds like nice bright coloured things and they come and eat them. Unfortunately, they don't really do birds any good. In fact, they kill them. So that's not the best thing. Children are like birds, and if they wander around the garden and see little blue things, if any of you got a little brother and sister, they're always putting stuff in their mouth. Well, actually, mammals, in this case people, it's toxic for them too. Less than they used to be. They used to be mercury, but nonetheless still not a good idea. And surprise, surprise, if you get these things in aqueous systems, slugs and snails are mollusks. There are many mollusks in aqueous water systems, as well as other types of insect which also don't like them. Then it's a poison, an aquatic poison. So it's actually quite a bad idea. I won't tell you the whole story of this. We don't need to. Let's go back a few years. I was in a chemical company, and we were looking at producing a product to go into the slug and snail killer market. Various work was being done, and the normal sort of process that happens where you look at what somebody else is doing and then you look to see if there's anything new around. The process goes like that. Well, by pure accident, we had greenhouses where we tested things, and we were growing tomato plants, which actually are beloved by slugs and snails, and we were feeding them with urea, or at least it was normally we fed them with like a more standard fertilizer, but we had some of this stuff left over. Didn't make any sense to waste it, so we watered this greenhouse with urea, except for when we ran out. So there was some that were watered with urea and the rest were not. And the slugs and snails were let loose in the greenhouse, and guess what? The accidental discovery we made was the slugs and snails wouldn't go anywhere near the tomato plants that had been watered with urea. They were going for the other ones. So we did a few more tests, and it wasn't quite the great news story that it might have been. But clearly, urea was interesting, because if you watered plants with it, slugs and snails weren't interested. They got interested again after a couple of days, but quite soon after you watered them, compared to watering with anything else, any other fertilizer, they avoided it. It is a double whammy, this one, because urea is a fertilizer, which means the plants can take it in through their leaves, or as it gets oxidized in the atmosphere, it becomes nitrate, and the plants feed on it again. So this was a double whammy. So in one sense, it would have been really great to stop using something like this, which is nasty and toxic, and instead use urea, which is pretty much okay to use, and solve the problem, and actually solve a problem that wasn't there to start with as well, which was feeding the plants. But in the end, it turned out not to be as good news as we'd hoped. The protection period for the plants was simply too small. Anyway, you get the point of the story. It would have been wonderful to replace this poison product with a pretty much non-poisonous product and have the same effect. And that's usually the problem. It's getting the efficacy, the same effect that you will get with the poison that you're making with a non-poison. Okay, so less hazardous chemical synthesis is the third principle. The fourth principle is actually safer solvents and auxiliaries. So now you're not thinking about the main reactants you're putting in, you're thinking of all the other stuff that you put in to make your product. Basically, they need to be cut down or made unnecessary. And if you do have to use them, you have to use something innocuous. Now, there is a particular area here which is quite useful, which is, and I'm not going insane, aqueous organic chemistry. I'm going to use a slide later in a very cognate part of the course. But if you look at what the types of requirements you have to meet this principle, mostly we're making organic compounds. And by definition, that means you're using organic solvents. Most of these are expensive, and they're an environmental problem of one sort or another. Before they even arrive at your factory gate, that's what we were talking about before, most of the solvents have already got invested in them considerable energy and considerable environmental damage that's already been done in making them. On the other hand, water is easily reusable, easy to clean up, and freely available. So an example of a beneficial solvent would be water. And one of the logical types of reasoning here would be, okay, can we do the chemistry that we're doing currently in organic solvents? Can we do them in more environmentally friendly, more cheaper solvents, for instance, water? And as I was saying, there's a growing body of knowledge now about aqueous organic chemistry, and it's a different subject. The rules are different, and we'll look at some examples in a while. The problems with this particular principle is there is no standard measurement index, and there are always going to be trade-offs between, okay, we'll use that really bad stuff for using this and things like that. Ironically, particularly important when you use catalysts. But anyway, more of that later. Okay, let's go on to the fifth principle, which is design for energy efficiency. Now, there's a number of ways to think about this. we'll think firstly about your chemical process, the thing you're doing to make your product. And there it's quite easy. So if you have to heat something, then maybe you might want to think about not heating it traditionally, but maybe using microwave radiation. So you get much more efficient use of the power. Or you might want to say, okay, let's not heat it at all. We can do this reaction thermochemically. Again, much less energy. So you need to think about other ways to break a bond or to move an electron. When you heat something, it's like hitting something with a hammer. You're putting an awful lot of force in, and hopefully if you hit it hard enough it will break, type thing. But it's usually reasonably indiscriminate, because all you're doing is you're putting energy and you're building up energy levels, and ultimately you then are able to break the bond. With something like photochemistry, it's much more tailored. You're putting energy just in to the bond that you want to break, which means it's a lot cheaper in energy terms. Okay, so that's the first part of thinking about energy efficiency in reactions. So to reduce energies required, you might use catalysts. You might use enzymes, which both of those would lower the activation energy of the process. You might use photochemistry. You might use sonar chemistry, or you might use microwave. There's a whole load of stuff here. And again, what we'll do is we have sections of the course on some of these, and we'll be studying case studies in there quite thick and fast. So you'll get to see exactly how that looks, what that looks like, and how useful it is. Of course, the other way to think about energy efficiency is your factory. Remember, good business is green business. So if you can use less electricity and therefore save money, or less water and therefore save money, but at the same time produce the same product with the same impacts or less impacts, that's good for the environment, that's good for your wallet as well. And going further afield, we're going beyond the principles now, but you look at how far you're truck and transporting your supplies or your products. Goes into a bigger story which we're not going to follow. But certainly in terms of the process and in terms of a single factory, this fifth principle flows exactly along the same lines as good business practice. Okay, the next principle, the use of renewable feedstocks wherever technically or economically practicable. Well, there are a number of examples, and again, this is another good business sense thing. It is now possible to make hydrocarbon fuels from carbon dioxide. The economics are not there yet, certainly for the inorganic chemically catalyzed type route, but if you do that using nature, for instance making biofuels from algae or rice chaff or trees, or in fact just using trees neat as fuel, as wood, these are all renewable resources. And one of the best examples I like is Lafarge Cement. They're the biggest cement company in the world, and making cement is very energy intensive. They managed to shift about 30% of their fuel, their oil they were using, to fire their burners and replace it with domestic waste. It reduced their emissions, it reduced their fuel costs, and it improved the product. Again, good business is green business, and certainly in this module you're assignments you're going to get for your projects, your feedstocks, you'll learn all about this there, so I'm not going to spend too much time talking about it here. Okay, the next principle, the seventh principle, is about reducing derivatives. You understand what I mean when you're doing an organic or even an inorganic synthesis. You have to use blocking groups or protect or deprotect. You have temporary modification and good knows what on your way to get to your final product. Now, all of these steps require additional reagents, additional energy, more time, and they generate waste. So the seventh principle is basically these should be minimized or avoided if possible. And I've got a little example for you. This is a preparation of a synthetic penicillin. Now you've got two routes. You can start with penicillin G, and then we can go this way, which is the traditional way. So you use various blocking agents and reactions at -40 to get your penicillin G into derivative number 1. And then you then use M-butanol at -40, then water at 0 to affect your product that you're looking for, which is 6-APA. 6-APA is one of the major routes to synthetic penicillins, so it's quite important. Now you can do all that and work out how much reagent you're using, what species you've had to buy, reagents you bought specially to do that, and the time and the money. Or you could pay a little bit more for an enzyme and go in one step at room temperature, straight from your penicillin G to your 6-APA. That's the type of situation or the type of solution that I would call a green chemical solution. Now, it's actually, the actual example is related to the next principle as well, but you see the point. Make the process as simple and straightforward as possible. Okay, enzymes are actually only biological catalysts, but let's this is one of the main thrusts of green chemistry. Catalysts or catalytic reagents are superior usually to stoichiometric reagents. Now if we think about what a catalyst does or a catalytic reagent does, usually it reduces the activation energy, so it makes the reaction easier to go, less energetic, and provided you used a catalyst which is reasonably selective, also you save the types of steps we were looking at in the previous principle. Okay, and in principle at any rate, catalysts can be used in small amounts and recycled indefinitely. That's not true. All catalysts get poisoned, but largely you're not using stoichiometric amounts of catalyst. Okay, here's a little example then. Example of acetophenone. You want to reduce the ketone group to an alcohol, so sodium borohydride, off you go, bang, and you end up with your nice reduced ketone is now an alcohol, and your boric acid and sodium hydroxide as a side product. If you do the sums, that's got an 81% atom economy. On the other hand, you can take your acetophenone, you can add hydrogen and run it over a palladium on carbon catalyst, and you get your product at 100% atom economy. No side products, no waste. So the more of this latter type of thing you can do, clearly the more economic and the better off you're going to be. The environment often has problems, and in fact often species that we make, weed killers, pesticides, they're designed to be persistent, because if they're persistent, they're there longer and they can kill whatever bug or whatever they're trying to kill. This principle is design your chemical products with degradation programmed into them. So slightly different, but just to explain what I mean. A long time ago, it feels like sometimes in a different world, one went to buy, for instance, a toaster or something like that, and if it broke down 3 or 4 years later, you would take it back and they would repair it for you. And things were designed to last a long time. Cars were designed to last a long time. Which, in one sense, you can see the business problem here. If you make a car and it lasts 20 years and it still looks great after the end of 20 years, then what incentive does your customer have for buying another car before 20 years? Anyway, that's the business thinking that's happened. So now stuff is designed not to last. It has a specified design lifetime, in which can then after that, the idea is you go and buy another one. Now, for some chemicals, as we were just talking about, that function of long lifetime is good for their function, and that's great. But often in the environment, our problem is that you have many different types of chemical, which maybe are not designed. They don't have to be there a long time for their function, but they are persistent in response to the bacteriological and the biological and chemical degradation mechanisms. Okay, so let's take these two molecules. They're alkyl benzene sulfonate, and in fact they're used in things like detergents and surfactants, amongst other things. The molecule on the right has a high degradation rate. It will degrade quickly. The molecule on the left is very persistent. It will stay in the soil, for instance, for a very long time and degrade only very slowly. So obviously, one has to think about what products and how you're applying it, but design degradation at the molecular level into your products. Okay, we're getting to the end of these now. The next principle is to, if you like, prevent the formation of hazardous substances, prevent the formation of waste in your process by in-process real-time monitoring. Now, this is for most flow systems already industry standard. You typically have quality control actually plumbed into your reaction line. So typically you're measuring pH, maybe near infrared absorption, or maybe UV absorption, or temperature, or pressure, or cloudiness, you name it. All of these are routinely used process monitoring devices or systems, so that if the pH begins to move away from what it should be, the process standard, you know something's changing, and you can actually stop. You can either modify the process on the hoof, or if need be, you can shut the thing down before you've spent a whole day producing product which is going to be substandard or non-functional. That will then have to go to waste, and actually resolve the problem almost at source. This is trying to find a picture which would be anything other than tubes with a little window in was quite difficult. So this is actually a similar system which sorts polythene bottles, but you've got near infrared and it's being scanned all the time, and when you get a different in this case different polymer, it just pushes it into a different bag, but nonetheless exactly the same principle on a flow-through reaction system. Yeah, there's nothing much more I want to say about that. Inherently safer chemicals, or safer chemistry rather, for accident prevention. Now, it seems to me that some of these principles are very close to each other. So typically, substances and the form of a substance used in a chemical process should be chosen to minimize the potential chemical accidents, including releases, explosions, fires, poisonings, and the works. So we go back to our solvents. Now, when you work with organic solvents, which most organic products use an organic solvent system, you have all of these problems. You have explosions, you have fire explosions, fire risk, explosion risks, and poisoning, or worse, partial poisoning where staff or personnel become not fully functional. Okay, I'd like to draw your attention here. This is some work by Professor Kobayashi from Tokyo University Department of Chemistry. He's been developing pretty much organic chemistry in aqueous media. Now, so this is alpha, beta, gamma, delta unsaturated carbonyl compounds, and you've got a whole tranche here. I just chose this slide because it had a number of different compounds on it. Look at these yields: 91%, 87%, 93%. I must reiterate, I don't remember with organic chemistry ever getting yields that high. But nonetheless, this type of approach reduces organic solvents because suddenly you haven't got any. So you're running your process aqueous, which has got to be a good thing. So you've both replaced your solvents and you've made your process safer. That seems to me like the sort of result I like when I'm doing a project. Okay, we're going to end this one in a moment. The summary, I suppose, is inherently safer chemistry for accident prevention. Most accidents are combinations of different chains of events which don't necessarily have any link or belong together. So let's first of all look at this pyramid. So increasing effectiveness or safety is going up the pyramid, and there's a hierarchy of safety controls. The lowest is personal protective equipment. So it requires the worker to wear something: lab coat, safety glasses, goggles, whatever it is, steel cap shoes. The next level up is controls, administrative and work practice controls. So if you like, it's a QA system. This requires workers to do something. So, okay, I used to run a cyanide lab. The washing up was started always with soaking in hypochlorite solution to destroy the cyanide. That was part of the QA procedure, and so on and so forth. Above that are engineering controls, so certain stuff is prevented from happening automatically, mechanically, or with software. So that requires usually physical changes to the workplace. The obvious engineering control you probably are all familiar with is auto stops on lathes, so you can't put your hand close to the controller as the power just gets cut off. So it's effectively another level of safety. And finally, right at the top, which means it's also the most efficient place to start, because the further down the pyramid you go, actually the more change and often the more expense, is to eliminate the exposure before it can occur. And that's what green chemistry is about. We're literally at the peak of trying to stop problems before they begin, be it the environment or be it people. Usually a safer environment, a safer work environment is safer for the people, the workers that is, but also usually safer for the surrounding environment as well, because when you start designing a workplace for safety, you don't routinely have nasty chemicals flowing across the floor into the drains. And if the workplace is safer for the workers and the environment, then generally it's safer for the general public as well. Okay, I'd like to finish this first half by just reminding you about the metrics that we looked at that have arisen in this lecture. There's a couple we haven't talked about, but they're fairly obvious in one sense. Carbon efficiency, which is very, very much like the where have we gone? Rather like the percent atom economy, except we're just interested particularly in carbon, and a few others down here. And I've given you some guidance as to what's good and what's bad with those metrics. If we look at the chemical industry as a whole, what we've got here is the different sectors, their different waste structures, and therefore their different impact on the environment. So if we start with the E factor, and remember on the last slide, the E factor, the lower it is, the better it is. So oil refining has a very low E factor, relatively small amount of waste generated per product formed. Bulk chemicals is higher, fine chemicals is higher again, and pharmaceuticals is higher again, for the reasons that we talked about earlier, where the more derivatisation you have to do, the more purifications you have to do, then the more waste you generate. So clearly then your EF is going to go up. It's worth noting that these are the annual production figures in tonnes, and these are the waste produced in tonnes. So you can see that actually it's huge amounts, huge tonnages of oil, relatively to that little tonnages of waste. It's because everything in an oil refinery is used. Most times, okay, you do flare stuff off sometimes, but most things you are refining and using and then using as feedstock for something else. There are many metrics. I've talked to you about the most widespread ones, the ones you'd like to come across, but these metrics are often developed in-house by companies, and so there's some that you're never going to know anything about until you meet them, because it's that company's particular metric. There is one other that I've not talked about, simply because there's very little consensus about it. It's usually called a potential environmental impact or environmental quotient, and basically you take your E factor and you multiply it by a factor Q, which you could think of as an environmentally unfriendliness factor. So a Q value of 1 would indicate a very low degree of impact, because then the potential environmental impact would equal effectively the E factor. However, so you might think of water as being a relatively low environmental impact factor. Sodium chloride, which is not quite as benign, it does depend where you are, might be a little bit higher than that, it might be 3. But for some species which has major environmental impact, we'll stick with just inorganic chemistry now, maybe sodium dichromate or something like that, it might be 1,000. You can see already the weakness of this. How do you objectively assign a Q value to any particular substance? And it depends where you are as well. So there's no real consensus on this, and therefore I'm just giving this to you for information. You can find some other metrics around, usually in the planning or engineering world. I'm not going to talk about them. They are usually metrics to indicate environmental impact. Here is, if you like, the underlying summary. They're useful tools, and in some parts of your working life you may well get to use them. Okay, that ends the first part of this lecture. I'm going to end this now, and we'll begin the second part in a moment. Thank you for listening. See you later. Bye-bye.